So you've seen videos of chemicals exploding or changing colors, but what's really going on? This is where chemistry gets powerful. We're going to answer two huge questions. First, why do reactions even happen? What makes two substances like sodium and chlorine react so violently to make simple table salt? This part, covered by standard HS-PS1-2, is all about electrons and patterns in the periodic table. The second question is, how much? If I want to make 50 grams of salt, how much sodium and chlorine do I need? I can't just guess. That's stoichiometry, a big word for the recipe, the math behind the reaction. By the end of this, you'll be able to predict why things react and how much you'll get. How do you know a chemical reaction is actually happening? It's not always a big explosion. A reaction is any time chemicals change their identity by breaking and making new bonds. We look for clues or signs of a reaction. If you mix baking soda and vinegar, you see bubbles. That's a new gas being formed. When you use a hand warmer pack, it gets hot. That's a temperature change, releasing energy. Other signs are a change in color, like when a shiny nail turns reddish-brown with rust, or when two clear liquids are mixed and suddenly a cloudy solid appears. That solid is called a precipitate. These clues tell you that the original atoms are being rearranged into something new. In any chemical reaction, you have two basic parts, the before and the after. The before chemicals, the ingredients you start with, are called reactants. The after chemicals, the new stuff you make, are called products. We write this like a math equation, but instead of an equal sign, we use an arrow that means yields or produces. Think about grilling a burger. The reactants are the raw meat, the heat, and the oxygen from the air. The products are the cooked burger, the smoke, and the heat given off. In our methane example, methane and oxygen are the reactants you burn. The products that come out are carbon dioxide and water. This is the single most important rule in all of chemistry, the law of conservation of mass. It simply states that you cannot create or destroy matter. Atoms don't just disappear or pop into existence during a reaction. All the atoms you start with must be accounted for in the end. It's like building with Legos. If you have a pile of 10 red bricks and 5 blue bricks, you can break them apart and build a new spaceship. When you're done, that spaceship still contains 10 red bricks and 5 blue bricks. They're just in a new arrangement. The total mass of your pile of bricks is the same as the total mass of your spaceship. So if the law of conservation of mass is true, our equations must reflect it. When we first write an equation like H2 plus O2 rewrite to H2O, it's just a skeleton equation. It tells us what reacted, but not how much. If you count the atoms, you see 2 oxygen atoms on the left, but only 1 on the right. 1 oxygen atom has vanished, which is impossible. An unbalanced equation is like a recipe that just says combine flour, eggs, and sugar to make a cake. It's useless. How much of each? Balancing the equation is like adding the numbers. 1 cup flour, 2 eggs, half cup sugar. It makes the equation chemically correct and obeys the fundamental law of conservation. So, how do we fix the unbalanced equation? We use coefficients. These are the big numbers you write in front of a chemical formula. When we write 2H2O, that 2 is a coefficient. It means 2 molecules of water. This doubles everything in the molecule, so we now have 4 hydrogen atoms and 2 oxygen atoms. The most common mistake students make is changing the small numbers, the subscripts. You cannot do this. If you change H2O to H2O2 to get your extra oxygen atom, you haven't balanced the equation. You've changed the product from water to hydrogen peroxide, a completely different and dangerous chemical. Always use coefficients. Never change the subscripts. Let's walk through one. Burning methane, CH4, and oxygen, O2. The products are CO2 and H2O. First, let's tally the atoms. On the left, 1C, 4H, and 2O. On the right, 1C, 2H, and, wait, 2 O's in CO2 and 1 O in H2O. So 3 O's total. This is a mess. Let's balance it. Carbon is already balanced, 1 to 1. Let's fix hydrogen. We have 4H on the left and 2H on the right. We can fix this by putting a 2 coefficient in front of H2O. Now our equation is CH4 plus O2 returns CO2 plus 2H2O. Let's retally. Left, 1C, 4H, 2O. Right, 1C, 4H, 2H in water, plus the 2 O's in CO2, so 4 O's. We're close. Now we just need 4 O's on the left. We can put a 2 in front of O2. The final balanced equation is CH4 plus 2O2 returns CO2 plus 2H2O. We can balance equations, but that doesn't tell us why they react in the first place. The why is all about electrons, specifically the valence electrons. These are the electrons in the outermost shell or energy level of an atom. You can think of the inner electrons as the core of the atom, but the valence electrons are its hands. They are what the atom uses to touch, grab, and interact with other atoms. An atom's entire chemical personality, whether it's reactive, stable, a metal, or a nonmetal, is determined by its number of valence electrons. So what's the goal of these valence electrons? Stability. Atoms are happy when their outermost shell is full. For most atoms, this means having 8 valence electrons, which we call an octet. The atoms on the periodic table that already have this perfect setup are the noble gases, like neon and argon. They are stable, snobbish, and don't react with anything. Every other atom on the table is trying to become like a noble gas. They will do whatever it takes, give away electrons, steal them, or share them, just to get that happy full octet. This desperate drive for a stable octet is what causes chemical reactions. This is where the periodic table becomes a cheat sheet. It's organized by valence electrons. Look at group 1, the alkali metals like sodium, Na. Everything in that column has just one valence electron. They are desperate to lose that one electron to get to a full shell underneath. This makes them extremely reactive. Now look at group 17, the halogens like chlorine, Cl. Everything in that column has 7 valence electrons. They are just one electron away from a perfect octet. This makes them desperate to gain one electron. This pattern of wanting to lose or gain electrons is the key to predicting how elements will behave. Let's add one more trend, electronegativity. This is a big word for a simple idea, electron greediness. It's a measure of how badly an atom wants to pull electrons towards itself when it's in a bond. This greed increases as you go from left to right across the table. Why? Because you're getting closer to that stable octet, so your atoms get greedier. Fluorine in the top right is the greediest element of all. The metals on the left side have very low electronegativity. They're givers, not takers. The difference in this greediness between two reacting atoms tells us exactly what kind of bond they're going to form. So what happens when an electron giver, a metal like sodium, meets an electron taker, a nonmetal like chlorine? The electronegativity difference is huge. The super greedy chlorine doesn't want to share. It just steals the single valence electron from the sodium atom. Now the sodium has lost an electron, making it a positive ion, Na+. The chlorine has gained an electron, making it a negative ion, Cl-. Just like magnets, these opposite charges, plus and minus, are now powerfully attracted to each other. That attraction is the ionic bond. It's a total transfer of electrons. But what happens when two greedy atoms meet? For example, two nonmetals like hydrogen and oxygen. The oxygen is greedy, but the hydrogen is pretty greedy too. Neither one is strong enough to steal an electron from the other. So they compromise. They agree to share electrons. This sharing creates a covalent bond. Both atoms get to count the shared electrons as part of their own octet, making both of them stable. This is how most of the molecules you know, like water, carbon dioxide, and sugar, are held together. It's a partnership, not a theft. Now that we know why reactions happen to get a stable octet and how they bond, ionic, covalent, we can look at patterns. The simplest reaction type is synthesis. This is a building reaction. Two or more simple things combine to make one new, more complicated thing. The pattern is A plus B, return AB. Think of it like building a Lego car. You have the wheels, A, and the car body, B, and you click them together to make the car, AB. A real-life example is iron rusting. Simple iron atoms, Fe, combine with simple oxygen molecules, O2, to create a new, more complex compound, iron oxide, Fe2O3, or rust. Decomposition is the exact opposite of synthesis. It's a breakdown reaction. You start with one complex molecule and it breaks apart into simpler pieces. The pattern is AB replacing A plus B. This is like taking your Lego car and breaking it back down into the wheels and the car body. A great example is hydrogen peroxide, H2O2. It's unstable. If you leave a bottle of it out, the H2O2 will slowly decompose into two simpler, more stable things. Plain water, H2O, and oxygen gas, O2. That's why it bubbles when you put it on a cut. It's decomposing and releasing oxygen gas. These next two are like a high school dance. First is single replacement. This is when a more reactive element cuts in on a compound. The pattern is A plus BC leads to AC plus B. Element A cuts in, bonds with C, and kicks B out, leaving it all alone. This only happens if A is more reactive than B. Then you have double replacement. This is when two compounds in a solution swap partners. The pattern is AB plus CD leads to AD plus CB. The A from the first couple leaves with the D from the second, and the C from the second couple leaves with the B from the first. This often happens when two liquids are mixed, and one of the new pairs, AD or CB, is a solid, a precipitate, that falls out of the solution. Okay, we've covered the why and how of reactions. Now we switch gears to the how much. This is stoichiometry. It sounds scary, but it's just the math for a chemical recipe. You wouldn't bake a cake by just dumping random amounts of flour, eggs, and sugar in a bowl and hoping for the best. You follow a recipe, 1 cup of flour, 2 eggs, etc. A balanced chemical equation is that recipe. Stoichiometry is the process of reading that recipe to figure out, if I want to make 3 cakes, how many eggs do I need? Or, if I only have 100 grams of flour, how many cakes can I make? It's the quantitative, real-world math of chemistry. To use our recipe, we have a problem. Atoms are way too small to count. We can't put 2 atoms of hydrogen and 1 atom of oxygen on a scale. We work in grams, which is a huge number of atoms. We need a way to bridge this gap. That bridge is called the mole. A mole is just a word for a specific number, like a dozen means 12. A mole means 6.022 times 10 to the 23rd particles. This giant number, Avogadro's number, is special. It's the number of atoms in a certain mass of an element. We get that mass from the periodic table. For example, 1 mole of carbon atoms has a mass of 12.01 grams. This molar mass lets us convert from grams, what we can weigh, to moles, what our recipe uses. This is the most important concept in stoichiometry. Go back to our balanced equation for water. 2H2 plus O2 is 2H2O. The big coefficients, the 2, the 1, which is invisible, and the 2, aren't just counting molecules. They are counting moles. This recipe tells us To make 2 moles of water, you must react 2 moles of hydrogen with 1 mole of oxygen. This is the mole ratio. It's a fixed conversion factor. If you want to make 4 moles of water, you'll need 4 moles of H2 and 2 moles of O2. If you only have 0.5 moles of O2, you can only make 1 mole of H2O. This ratio is the heart of every calculation. So let's put it all together in a roadmap. A typical problem will be, if you burn 50 grams of methane, CH4, how many grams of water, H2O, will be produced? You cannot ever go directly from grams of CH4 to grams of H2O. You must use the mole ratio from the balanced equation. So you follow a 3-step path. Step 1. Convert your starting amount to moles. Convert grams of CH4 to moles of CH4, using the molar mass of CH4. Step 2. Use the mole ratio. Convert moles of CH4 to moles of H2O, using the 1:2 ratio from the balanced equation. Step 3. Convert your final amount back to grams. Convert moles of H2O to grams of H2O, using the molar mass of H2O. That's it. Grams to moles, back to grams. That's stoichiometry.